Okay. Wait, no, I want that there. All right, so today we're going to continue our look at exponents and logarithms. Specifically today we're going to look at exponential word problems. That is like applications of exponents, okay? And then tomorrow we'll look at logarithmic word problems and applications of logarithms and stuff like that, okay? So this is organized in thusly, okay? We're going to start here and go this way. Okay, it's like page 1. This is page 2 over here, and then you flip over to the back, page 3, and then these are going to be your homework problems right here. Okay, and you're not going to do all of these. You won't do all of these. I think I allow for choice. I think I have you pick 6. Yeah, you're going to pick 6 from the worksheet here. I don't think so. I think it's just these. It's just these. Yeah. So. I know Ryan really wanted some book problems in addition, but I'm sorry, Ryan. Maybe tomorrow. Okay.
Maybe for your birthday.
All right. Maybe for your birthday. That's right. Oh, July birthday.
It's okay. It's a gas station, so it's fine.
Oh. Okay.
You work at a gas station?
No, it's the name of the gas station.
7-Eleven. You can go get a free Slurpee on your birthday. Every birthday you get free Slurpees. That's pretty nice.
Yeah. It's like a win-win.
Yeah. My wife's born on the 4th of July, so she eats fireworks every birthday.
Oh, that's cool. My friend was born on
All right. So here we go. One major application of exponential word problems, or one way we'll be seeing them show up, okay, is compounding interest. Okay, so this is one application here. The formula that we're going to be utilizing, well, there's 2 of them. Okay, so there is interest compounded n times per year. This is still in use today. Okay, still in use today. All right, at banks and things like that, your savings accounts, and it's very depressing to see how little interest you get on that money that they're holding for you, but there it is. Okay, and so there's a lot of variables in here, right? So, for example, A is the balance, okay, in the account, or you could also think the amount. At the final amount, you might think. Okay, so it's the balance in the account. P, you know what that stands for? Principal, the principal. Which is the original amount. Okay, and I think that's the spelling of principal, right? Principal, the word the word principal is a P-A-L and P-L-E. I think in this case it's the P-L-E version. Okay, which is the starting amount. Exactly. They're pals with the students. That's like Miss Clayball. All right. T represents time in years in this case. Okay. R, interest rate, annual interest rate. Annual. Okay. And of course, that interest rate will be written as a decimal. Okay, so you won't put in like 3 for R unless you mean 300% interest. That would be pretty awesome. Okay, and so for 3%, right, it'd be 0.03, right? And then finally, N is the number of times compounded per year. So, compounding n times per year, that's a finite number of times. Okay? So you will see different values very close to that. However, there is a way to determine compounded interest if it's being compounded continuously. That means at every instant, at every moment, you are earning a slight fraction of that total interest rate for the year. And the way that you calculate that is the A equals PE to the RT. PERT. Yep. PERT. All right, and the variables are the same as what we talked about over here. E is not a variable, remember, right? E is the number E that we use for that compounding continuously. Okay. idea. All right, so P is still the principal, R is still the interest rate, T is still time in years, A is the balance in the account after after a certain time. So let's look through some example problems here. Okay. Number one, a total of $12,000 is invested at an annual percentage rate of 8.3%. Okay, find the balance after 5 years if it is compounded quarterly and then also continuously. Okay. So, $12,000, we'll do it quarterly here. So that means, is it going to be, which of the two formulas will we have to use here for compounding quarterly? That'd be the first one, right? N times per year. So we'll say A, right? We're trying to find the final amount. So A. What's our P going to be here? 12,000, right? That's the initial amount. $12,000 times 1 plus, and then R, the interest rate, is going to be? Yeah, 0.083 or 0.083. Either way you want to say it there. Yep. I'll do the 0.0 part just because that's what I said first. Over. And then N, number of times per year. Well, if it's compounded quarterly, how many times is that?
4.
4 times. 4 quarters in a year. And a dollar, too. All right, so there's that. And then finally, for our exponents here, again, the N, number of times compounded, so 4 again. And then T is going to be? Find the balance after 5 years. So 5 for your T. Okay, so go ahead and take like 10 seconds, type that in your calculator, see if you can get the answer that you need, okay? And please do actually practice typing this in, or at least do it a couple times just to make sure that you're okay with typing things in, because I know you all can use your smartphones and stuff like that, but these calculators were developed back in the mid-90s before you were born. And so I think maybe even earlier than that, I don't know. But they haven't changed the operating system since at least the mid-90s, I can tell you, because that's when I started using them. And so, yeah, it's just a weird operation. Sure, they've added colors and things like that, but still kind of ugly. Yes.
Mr. Wood, what do you want us to round to?
Well, since this is talking about dollars and cents, probably 2 decimal places in this case, right? That would make the most sense. Pun. All right, so hopefully you got $18,000.95. Sorry, $18,095.43. Good, so you should go read that, right? $18,095.43. Okay. All right. Questions on any of that? Okay. So then the next one is compounded continuously. So we're going to use A equals P to the RT, of course. All right. Same scenario, but now compounded continuously. Okay. Bless you. So let's bless you. So hypothetically here, or let's hypothesize. Hypothetically, let's hypothesize here. We're going for the same amount of time, same interest rate, same starting quantity of money. Do we expect the compounded continuously to make more money, or the compounded quarterly to make more money by the end? Okay, so you can say continuously. Julie, can you give an explanation why?
Because
you have a intuition. It's going to be the continuous one. Okay. Anyone have a idea, or they want to give a shot at explaining maybe? So yeah, Parker.
If you're only adding to the value once every quarter, it doesn't seem right, but it seems like you'll get less money if you add to it each quarter rather than just add a little bit throughout the entire thing.
Yes. So that's basically the idea here. Okay, basically the idea. So quarterly means that you take your interest rate, divide it into 4, okay, and then you apply that fourth of your interest every 3 months, every quarter throughout the year, okay? And that's how they divide quarterly, okay? So you're like, okay, I can see how that would then add money. For continuously, you're doing an infinite number of applications, of that interest rate, okay? But you're taking the interest rate and dividing it by infinity. So that you can kind of see, it's like maybe it's not so obvious, right? In the first case, we're applying the interest rate 4 times, and we divided it by, each time we're doing a fourth of the interest rate. For the continuously one, we're applying an infinite number of times that interest rate, but it's 1/infinitieth, if that makes any sense, of the interest rate, okay? But, well, let's see what happens here, okay? So let's see what happens. All right, so we'll type this in here, right? So P was, again, 12,000. E to the R is then 0.083 again. And then times time is 5. Okay, and so then this will be, okay, by the way, E is on your calculator in 2 locations. If you press second ln, that gets you e to the x. But if you press second division symbol, then you also get e. You just get the number e by itself without an exponent or anything like that. So you can choose which one you want to use there, but I'll use this one. Okay, so again, 0.083 times 5, and you get 18,172.45. If I round there. Of course, your banks and everything else, they will round down. You do not get those extra hundredths of a cent. Okay. So those extra hundredths of a cent are kept by your bank or other institution. You don't get them. You ever seen the movie Office? Anyone seen the movie Office Space before? Yes. Okay. So do you remember much about the movie at all?
I remember everything.
Oh, you remember everything? Okay. So like this is like that idea in Office Space. It's a comedy, but it's based off these guys, and they like decide to write a program that takes all those fractions of a cent that you see here. They take the fractions of a cent and they put them into a separate account and then accumulate them, and they end up getting in big trouble for that. And hilarity ensues and all that stuff. So anyway, so that's illegal. All right. You can see here, so you do make a little bit more money. So Julia Partner, you guys are right. Okay, you do end up making a little bit more money there. Okay, not too much more, but hey, it's better than the other one. So, all right. So the next one here, we'll try one. So find the number of years. This is different now, right? We're not trying to find the final amount. We're trying to find the number of years, which means we're going to be solving for what variable here? T, right? Because T is number of years. So we're going to solve for T. Okay, solve for T. Required for a $3,000 investment to double at a 7% interest rate, compounded, first do monthly, and then we'll talk continuously. Okay, so let's set this up. We know our $3,000, what is that going to go in for? What variable is that going for? The principal, right? It's the starting amount. Okay, compounded, let's see here, we're talking monthly. Okay, so let me go back to this. 1 plus our interest rate is 7%, so 0.07. Over n, so compounded monthly, there are how many months in the year? Good. Okay. And then our n, number of times per year, 12 times t. So, that's what we're solving for is t, right? All right, we still have one more missing piece of information, though. What is a?
6,000.
Wait, why is it 6,000? Where are you getting that from?
Because it says double.
Right. We want to double our original investment, so we're going to put 6,000 over there. Okay? So, how should we go about solving this? What should be our first step? Divide by 3,000, and you'll get 2 equals 1 plus 0.07 over 12 to the 12t. Okay, and now at this point, we got to get that t out of the exponent. What should we do? What can we use to get that t out of the exponent? Logarithm, okay? You can use log base whatever you want. If you want to use log base 10, that is the common log, right? If you want to use natural log, okay, ln, whichever one you want here. You could do log base 1 plus 0.07 over 12 if you like. That's kind of messy. I'm going to use natural log here. And so that 2t, 12t, will be able to come out front. So it'll be 12t natural log of the quantity 1 plus 0.07 over 12. Okay. So again, the 12t would have been the exponent, but I used the property there to kind of bring that down out in front at the same time as taking the natural log of both sides. Okay? Final step, what do we got to do? Divide both sides by 12 and the natural log of 1 plus 0.07 over 12. So t is exactly, it is precisely the natural log of 2 over 12 times the natural log of 1 plus 0.07 over 12. Okay? That is the precise answer, but of course for our purposes that's not very helpful. So we're going to get a decimal here to get the number of years. Type this in my calculator. And again, if you don't feel super confident, make sure that you practice. Or if you do feel confident, but you still want to just check, make sure that you can type this in your calculator accurately. Very important. Okay, I get about 9.931. Years. Okay. And this is where it can get a little bit tricky about, how you're supposed to answer the question. All right, we could probably answer it just here and say, okay, after about 9.931 years, all right, we'll say that this, this happens. This takes place. Okay, you could say it happens in the 9th year, right? In the 9th year, because it's a little bit beyond 9. Or you could also say after 10 years. Okay, after 10 years, for sure it will be. Not after 9, after 10. Right? We round up here to say 10 years. So it really depends on the context here. On how you want to kind of answer that. But there you go. So you guys go ahead, take a minute or two, try letter B, okay? Solve for compounded continuously there. So set it up and solve for compounded continuously. Oh, question from me. The way you have typed in, your calculator is only going to divide natural log 2 by 12. But it says parentheses on your denominator. There you go. So it's only divided by 12 and then multiply the answer of natural log 2 divided by 12 times natural log of 1 plus 0.07. So you want that all in the denominator, you got to put parentheses in the denominator. So good for typing it in there too, because we get that caught now, as opposed to later. Make sure you're putting parentheses around your numerator, parentheses around your denominator too, okay? Especially on that denominator, folks. Super important. You have like 30 more seconds here, and we're moving on. All right, time, there you go. Should be about 9.902 years. So slightly less time, right? Slightly less time, which shouldn't surprise us, right? Because given the same amount of time in the same scenario, one being compounded quarterly, one being compounded continuously, we made a little bit more money in the same amount of time. So then trying to figure out the amount of time it would take to double an investment monthly versus continuously, we'd expect the continuous one to be less, okay? So expect to be less. Yes, Riley.
Can you please show how to put part A in the calculator, because I keep getting something different.
Yes. So did you put parentheses around 12 times natural log of 1 plus 0.07?
No.
So that's what you need to do, okay? Without the parentheses around it, Okay, so this is what I typed in. You have typed in this. Okay, like that. And you see is that what you got? 3.35 something? Yeah. So you need parentheses on the denominator. What your calculator is reading, Riley, what your calculator is reading when you type it in like this, it's saying it's reading natural log 2, divide by 12, and then take that quantity and multiply by natural log. You want to divide by the product itself, so you have to put parentheses around that. Okay? And so, again, thank you for typing that into your calculator and trying it out. Okay, this is why I suggested you do that stuff. So, good on you for doing that. All right, moving on. Any other questions before we move on? All right, HalfLife. HalfLife. Okay, probably seen this show up some in your, classes. I guess chemistry, is where HalfLife shows up. Maybe. So the half-life equation, there's several different ways to write this. The one that we're going to be using is this. Okay. Several ways to represent it, but this is the one we're going to use. Okay, where capital A is the final amount. Okay. This A with a little 0 here, that's called A naught or A sub 0. Okay, and that is the initial amount. Right? Typically, if you have a quantity represented by a variable, you can one of the typical ways of describing the initial quantity of that amount or initial quantity is to put a little sub 0 there. So A sub 0. Or any variable sub-0 means the initial quantity, initial amount there. Okay. Just like if you see a delta, if you see the Greek, triangle, little triangle in front of a variable, that means change in a variable. All right. Anyway, T, time in years. Okay, and then H is half-life, also in years. Half-life also in years. So just in case we're not familiar with the half-life idea, I'll just talk about it briefly here, right? So you all understand, right, that some things are radioactive, right? Some compounds are radioactive, and that means that they emit particles from them, okay, emit radiation. And as they emit radiation, they change from one element to another element, okay? And so as they emit this radiation, over time they change. And so the half-life is the amount of time it takes for a certain quantity to reduce to half its original amount. Okay? That's half-life, right? So we have an made-up element here called wittium. All right, the half-life of wittium is 40 years. If you have 6,000 grams now, how much will you have left after 80 years? Okay. Well, this one actually doesn't really require us to use a formula if we think about it, right? So after 80 years, how many half-lives will it have gone through? 2 half-lives, okay? So half and then half again. Well, what's half of a half? A quarter, right? A fourth, right? So if we take 6,000, we just multiply by 1/4, we get our answer there. It's going to be 1,500 grams. You see, every 40 years, it's going to be half its amount, okay? Half the starting amount after that, 40 years. So it's just 1,500. Now, of course, if you want to, you can start with the formula and say, okay, but Mr. Wade, what if we use the formula? So if you have like A equals 6,000, okay, because that's your starting amount there, times 1/2 to the, and then time is 80 over half-life here was 40. But what does 80 over 40 simplify to be? 2 and 1/2 squared, that's 1/2 times 1/2, 1/4 times 6,000, you're still going to get the same thing. 1,500, right? So you can see there. We're doing the same thing. Okay? All right, so then for letter B, though, slightly different scenario because now we're going over 135 years. So in this case, we would need to probably set up our equation here, right? So 6,000 starting amount times 1/2 to the t. In this case, t would be 135 over the half-life 40. Okay, and if you put that in your calculator, you're going to end up with something like 578.329 grams. Okay. Letter C, another application of it there. 400 years would be how many half-lives? 10 of them. So you have to do like half and a 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 half 10 times, right? So you do 1/2 to the 10th times that 6,000. It's going to be pretty small, 5.859 grams approximately there. But we're going to skip that. I'm not going to have us do that one. We'll just keep going here, okay? I think you get the point, right? Just plug it in the formula and solve. All right. This next one is kind of important for you guys because this is dealing with what we are talking about for our population projects, which are due Wednesday of next week. Okay, as you decided, as you wish. All right, so the population equation, as you are given it in your calculator, is a times b to the x. Okay. For the population of Mathistan, we should change that 2 in the exponent there to be an x instead. Okay. So the population of Mathistan can be modeled by the equation y equals 2.056 times 1.002 to the x. Okay, again, in this particular scenario, we round to 3 decimal places. I would highly recommend, highly recommend for your purposes that you give more than 3 decimal places. It just helps things be more accurate. Okay. Also, when you're doing your population projects, don't forget, right, sometimes that E shows up. That E means exponential, that E means scientific notation kind of thing, okay? So E something means times 10 to the, and then whatever that something is with the E there, okay? So in some cases, you guys are going to have like E and then the negative number or something like that, okay? So pay attention to that. That's important, okay? Don't cut off the E stuff. If you have further questions, let me know. Okay. So, what will the population be in 2010, right? So, or I should say, what was the population in 2010, right? 2010. All right. So, in order to do that, well, what are we going to do? Using our equation here, yeah, right?
You crossed out the square thing.
It's like, yes, make it an x instead of a 2. Yes, sorry. Make it an x instead of a 2. Yes, that's our variable x there. Okay. So, again, where should we put that 2010? What should we do with 2010? If we're trying to find the population in 2010, what should we do with that number? Well, remember here, in this scenario, y is the population in millions, okay, x is the year. So 2010, if we want to find the population, that means we're solving for y, and 2010 then is in x. So we're going to plug 2010 in for x. So it's like literally just y equals 2.056 times 1.002 to the 2010 power. Okay. So if you wanted to predict your population in 2025, for example, that's where you put the 2025 right there. Okay. And I get about 114.063, we'll say. Okay. But 114.063 what? Million people. Why is the population in millions? So this is million people. Or people in millions, if you like. Okay. Letter B, if there were 111.81 million people in 2000, in what year will the population double? Whoa, what a coincidence. That's like a question on our population project, having to figure out when our population in a certain year will double. It's pretty cool. All right, so Well, here's our equation. Y equals 2.056 times 1.002 to the x. We're trying to find what? What's the quantity we're trying to find here? The what? We're solving for what? When it will double. So when means we're solving for a year. In what year? So that means, sorry, and then, yeah, you guys, so what's the variable for that year? Or what's the variable for years?
Why?
Is it? Is it? Which one is it? Which one represents years? X. So we are solving for X. In what year? So we are solving for X, because X is the year, variable represents the year. So that means we need to plug something in for Y. What's going to get plugged in for Y, right? We need a population to plug in there. What goes in for Y? 111.81 times 2, because we're not interested in when the population was 111.81. We know that it was happening in 2000. We want to know when the population is going to double. So we're going to put 111.81 times 2 in the y, and then 2.056 times 1.002 to the x, like that. Okay, doubled population. Okay, and then we'll divide. Now we'll solve for the x. So we'll divide both sides by that 2.056. But can I multiply 2.056 together with the 1.002? Why not? They're just two numbers are being multiplied. This one is being raised to the x power. This one is not. So we have to divide it over. In fact, if you want to, maybe to help yourself out, put parentheses around that to kind of see there, right? So we'll divide the 2.056 over. That's equal to 1.002 to the x. And then again, you can use whatever logarithm you want. If you want to use log base 1.002, that's your choice. If you can use log base 10, log base 7, whatever. I'm going to use natural log just because. I'll go ahead and I'm going to go ahead and double the 111. So it's really 223.62 over 2.056. That's equal to the natural log x times the natural log of 1.002. Okay, and so we'll divide over that natural log, and we get x is exactly natural log of 223.62 over 2.056, and then that quantity divided by the natural log of 1.002. Oh, I see division between two logarithms. We can put that together, right? No, cannot. Right? Division between two logarithms, there is no property. But when there's division inside a logarithm, that can be changed to what? Subtraction. So be careful here, right? Natural log divided by natural log, no simplification, just do it, right? But natural log of something divided by something, that can be changed to subtraction if you like. Okay? The approximation here, I should say, it should be 2,346.939, I think. Retype this just to be sure. 2,346.937 is actually what I get there. Okay. Okay. So in what year will the population double? It'll be during what year? Yeah, 2346, I believe. 2346. But I'd probably also accept 2347 there too. Yeah. Okay. Question on any of that? All right, so there's an example of some of the work you need to be able to do. All right, flipping over to the back. Last one. Okay. Percent equation. Percent increase, percent decrease, right? So here we got another one. Similar kind of setup here. We'll have our final amount and our starting amount. Okay, 1 plus r to the t. So again, a is the final amount. A sub 0 is the starting amount, or initial amount. R is the rate as a decimal. And t is time. Okay? And so we'll go through some of these problems here. Number 5, for example, you buy a house for $500,000 the week after you get married. The value of the house is set to decrease at a rate of 7.5% per year. How much is the house worth in 10 years or 20 years? And we'll probably just do the 10-year one, and then we'll just, you'll get the idea from there, okay? So, all right, let's get the setup here then. So we're trying to find the final value of the house in 10 years. We're going to be solving for capital A, right? What is A sub 0 here? What's our initial amount? 500,000, 500,000. Okay, times 1 plus, what's our interest rate here? What's our rate? Okay, 0.075, but it's a decrease. So how should we represent a decrease with our rate? Negative. Yeah, so we'll do 1 plus a negative 0.075, or you can just do 1 minus 0.075, whatever you like. So I'm going to make it plus negative because I already put the plus sign there. Okay, to the t, and what's our t? 10. Okay. You type that mess in your calculator, and you'll get something along the lines of $229,291.17, something like that. Of course, 20 years, you'll be even lower than that, right? Because you're going to be continuing to decrease in value. Okay, questions on any of that? All right, number 6 then, the price of gasoline is set to increase at 3.5% per year. How many years will it take for the price to double? Okay, so now we're trying to find the number of years. How many years? We're going to solve for t. T is our unknown variable here. All right, but there's a problem because, well, if t is our unknown variable, we need to come up with values for all the other quantities here. Right, so, well, the only other number we have is this 3.5%. And where would that go? 3.5% is the what? It's the rate, right? So 1 plus 0.035, again, it's increasing at a rate, so add, positive there. And t is what we're solving for, but we don't have any information about where the price of gasoline starts or where it's supposed to end. We just know it's supposed to double. That's all we need to know. Let's just say that that's our initial amount, some unknown quantity. If it's going to double, what will the final amount be? 2a naught, right? Or 2a sub 0. And that's all you got to do to set that up. Okay. Letter B, increased by a factor of 8, then you'd have a sub 0, and then 8 times a sub 0 there. Okay. So now, when I go to solve here, what's going to happen to the a sub 0s? They're going to cancel because we're going to divide both sides by a sub 0. And so we get 2 equals whatever 1.035 to the t, like that. And then you can use logarithm, natural log, common log, whatever. I'll use common log this time just to change it up. So I'll say log of 2 equals t log of 1.035. Divide both sides by that log of 1.035. So precisely that, Okay, which is approximately 20.149, we'll say, and that's years. Okay. So if the price of gas only increases at 3.5% per year, then we expect in about 20 years for the price to double from where it was initially. Okay. All right, we'll do this last one here, number 7, and I'll just set it up. Okay, I'm just going to set it up. So the cost of a car 5 years ago was $10,000. It is currently on the market for $15,000. Maybe it's like a collectible car or something like that, right? What is the rate of increase for the value of this car? Okay. What is the rate of increase? That means we're going to be solving for R, the interest rate here. The final amount, $15,000. The original amount, $10,000. Okay, original value. Times 1 plus R to the, and then what's our time here? It took how long to do that? 5 years, right? So to the 5th. So how should we go about solving this and get R by itself here? What should we do first? Divide by 10,000 on both sides, you get 1.5 equals 1 plus R to the 5th. And then use a logarithm here? Actually, we don't need a logarithm here. How do you get rid of something to the 5th power? We root 5th root, right? 5th root. So yeah, we'll just do 5th root of both sides here. Okay. Now, there's 2 ways to do 5th root in your calculator. Option 1, if you press a 5 and you go to math and you go down, there's this little x root right there like that. So you can see I have 5th root now. Okay, so you type the 5 first, then you press math, you go down to that little symbol right there. That'll allow you to do the root of anything. So we'll do 1.5. But of course, the 5th root is the same thing as what exponent? Yes, to the 1/5 power there. And you can see the exact same thing. Right? 5th root, 1/5 power. So 1 plus R is approximately 1.084471771. And so R is approximately 0.084471771 kind of deal. Okay, so about 8% per year. We made it, just barely. Okay, sorry about that, folks. That was a little dry, I know, but we had to get through all those. Okay, so you'll have 6 to pick from over here out of the 11. Okay, 6 out of the 11 to pick from. Okay, including number 11, write your own original word problem. Okay, so anyway, 6 to pick from there. Okay, 6. Say what?
I'm very sorry.
Oh. It's okay. It helps me to know that my voice is soothing, and you feel safe enough to do that. Yes?
What is your favorite exact time of day?